Okay, so in this lecture, we're going to cover section 2.7. This is going to be on the derivative. So for now, we're just thinking of the derivative as a number that you can associate to a function. But in the next section, we'll see that the derivative itself is a function. So if you're given a function that's quote unquote nice enough, and we'll explain and we'll learn what that means in a moment, what nice enough means, then the function actually has a derivative. And this is going to be intimately related to a concept that we already looked at, and that's the concept of continuity. So it's going to turn out that any function which has a derivative, first derivative is going to be differentiable. All right, so let me share my screen. Hopefully you can see what I'm seeing. So, so yes, we're in 2.7. This is on derivatives and rates of change. We're going to look at tangent lines again, but let's return to the problem that we first looked at when we went over section 2.1. That was on velocity. So this is going to look hopefully familiar, and it's going to be basically the same discussion that we looked at before. So it turns out that the velocity is going to be the derivative of the position. So here's the setup. It's basically the same setup. We have an object moving along in a straight line, according to some equation of motion, f of t. So f is, again, remember, it's some function from, say, 0 to infinity. It doesn't have to be from 0 to infinity, but that's the easiest way to measure time. And then f of t is position. It's your position at time t. So and it'll be positioned along the real line, and so it's going to be relative to the origin rate, the origin to, 0. And so this function describes displacement or directed distance of an object from the origin at time t. And you remember that we wanted the motivating problem for calculus was trying to describe instantaneous velocity. So we know how to make change sense of average velocity. So it's just going to be the distance you travel, the change in position divided by the change in time. And this will give you this fraction, and then you can continue this process where you have a given instant of time where you want to know the instantaneous velocity, so you can get an average velocity over an interval of time centered, say, at that time you're interested in. And then you just continue to look at smaller and smaller intervals centered at that given instant that you're interested in, and you're going to get a better and better approximation of the time, the instantaneous velocity at that time. So you would take quote unquote limit of that ratio, that fraction, that average. You would take a limit of your average velocity, and we already saw how to make precise this idea of a limit. Well, it turns out that velocity is, as I indicated earlier, is just the, or sorry, yeah, sorry, the velocity is just is the derivative of the position. It's going to be the derivative of this function right here, f of t, with respect to time. So you have a time interval. So you have, say, you're interested at t is equal to a. We were looking at t sub 0, but it's the same idea. So this is like your initial time right here, t of a, and then you have some later time, t of a, t equals a plus h, where we're going to think about absolute value of h being small. So h is going to be some small number. And so that means that the distance from a, or sorry, not the distance, but the change in time, how the number of seconds or time units that elapse between a and a plus h is very small, because we have a plus h minus a is equal to absolute value of a. So the a's cancel out, right? This a cancels with this a, and all you're left with is absolute value a. And then we're starting with h, we're starting with an h such that the absolute value is small. So this is going to be small as well. So in other words, we're considering, when you add this h to a, you're considering points in time that are very close to that initial time a. And then now the average velocity, as we saw in the video on 2.1, is just going to be the displacement, the change in position, divided by the change in time, right? And the change in time we saw right here is just h. So that's why we have h in the denominator, and then we have f of a plus h minus f of a, because that's going to be your change in your position. And then this right here, this could be, for example, the plot of f of t. And basically, you're looking at this point on the curve right here. This is this is the point a comma f of h. And then you have some later time, say, this is if h is positive. Of course, h could be negative, and then you maybe be talking about a point down here. Because when you add a negative number, it reduces it, and so maybe it's like right here. But that's all right. It doesn't matter. You can just take h to be positive to simplify the discussion. So if h is positive, it's going to be this point right here. Um, and so this is going to be some later point in time. And if you compute what you're computing right here is actually the slope of this blue line right here. And this is how we connect to this so-called tangent problem, which we'll look at in a moment. But this will be an average velocity, this number right here, by definition, which is also the slope of that, this, not the tangent line, but the secant line. The red curve is going to be your tangent line. And then what happens is you are going to take a limit as h goes to 0, and this point right here is going to kind of like slide along the curve. And then each time you slide, so in other words, you slide the point in time closer to A. So in other words, you shrink h a little bit, and then you compute an average velocity, and then you shrink a little bit more, which has the effect of sliding that point further closer to this point, and then you compute another average velocity. You just keep repeating this process, and you'll get a sequence of average velocities, and then you'll take a limit, and that's exactly what the instantaneous velocity is. So this instantaneous velocity is going to be this limit right here of your average velocity. So this right here is your average velocity. And then you're taking h go to 0 to get a better and better limit. Sorry, better and better approximation of the instantaneous velocity. And then the instantaneous velocity just is by definition the limit. And of course, this is only the case if the limit exists. But if you're talking about velocity of a physical object, it's going to exist usually. Motion of physical objects is continuous, at least, and in fact, it's actually differentiable. The position of your so yeah, the position is going to be not only just a continuous function, but it's going to be a differentiable function if you're talking about the motion of a physical object. So let's see. All right, so now that's the average velocity. So and then the notation you use is just v of a. Usually we don't use f of t. We usually use p of t to denote position, but that's okay. It doesn't matter. And then the other problem is the tangent problem. So let's scroll up a bit. So we have tangents. So basically what you have is a curve. And it's going to be basically the same idea. It's very much related. So you have a curve C, and it's described by this equation, y is equal to f of x. And you want to find the tangent line to C at some point, a comma f of a. And so basically what you do, first of all, you can compute the slope of the secant line. So you take some point, you take a nearby point, which is almost like taking a point in time close to this point. This is maybe a little bit more general, talking about tangent lines. But you just take a nearby point, and then you take where the point isn't the same. So you're not talking about the same point, but just a point close by. Then you can compute the slope of the secant line, like as indicated here. And what this amounts to is you have a curve, say, right here, and there's the initial point, and then this is some nearby point. And then you can draw a line through them. The whole line isn't drawn, but you can see there's this blue line segment. And this is going to be the secant line through this point and this point. and then you get what this number right here computes is the slope of that secant line, this blue line. And then what happens is, so now to get the slope of the, sorry, to get the slope of the tangent line to this curve at this point, is what you do is you just take a limit of these slopes of secant lines. So these are slopes of secant lines. This you're taking like basically like what you do is you take a point nearby and then you compute this the slope of this secant line, and then you take this point again, and then you slide it closer, maybe here, and then you take this line. Hopefully you can see what I'm drawing. It's a little bit, it's now goes through this point right here, like that. So it slides towards this point. You compute the slope of that line, and then if you just keep repeating this process, you're going to get this sequence of slopes of secant lines, and you're going to take their limit. You're going to see what value they're approaching. And that's just going to be by definition the slope of the tangent line, this quantity right here. And you can see right here, this is like a graph kind of illustrating what's going on here. So you have this initial point that you consider, and then you can the point Q, which starts here, is like this variable point. It's like a point nearby, and you just keep sliding it along. So you have like these blue lines are all these blue lines are secant lines whose slope you can compute, and then the red line right here is the tangent line, and the slopes of these secant lines are approaching the slope of that tangent line. And that's exactly what this right here is saying. You have these slopes of these secant lines, which I circled. This circled thing is the slopes of these secant lines, and then you take the limit and then you say that the slope of the tangent line is just like the thing that these secant lines are approaching, the slope of these secant lines are approaching. Um, so let's look at this example. I think this is a pretty simple example. Um, Actually, we looked at this example before. I don't remember which section, but now you can interpret this. There's another new way of interpreting this problem. It can be interpreted as finding the slope of the tangent line. Before we just treated it as just a limit of some function, and that was fine. But now we can reinterpret what this quotient means, and it's going to be the quotient of the secant line to the curve x squared at this point. Maybe they have a graph somewhere, I guess. Yeah, I guess they do. It's kind of, all right, anyways, it's not really that great of a graph. But you can see the algebra is pretty easy to find it. So you just factor this numerator and then you can cancel. So there's this x minus 1, you cancel here with that. And then all you're left with is x plus 1. And now this is a polynomial, it's continuous. So to evaluate this limit, you just plug in 1 and you get 2. So in other words, what we're doing, let's see if I can draw it, is you have this parabola, it goes like this, and then maybe like 1 is right here. And then you're looking at this tangent line, and that tangent line has slope of 2. So the slope of this line, slope of this tangent line, 2. So in other words, we have two different ways of interpreting the derivative. We can interpret it as the slope of a tangent line, and or we can view the derivative as this as the rate of change of some quantity. In most cases, in the cases we've been looking at, it's just the rate of change of your position. Now, there's another interesting thing to know about this. The derivative, which is the slope of a tangent line, is that it gives you an approximation of the curve, and this is what it basically means to be differential for a function to be differentiable. I haven't talked about differentiable functions yet, but this is what it's going to be what it means to be differentiable is that when you take your curve, so here you can see this is the parabola, this is a graph of the parabola, and we're just going to zoom in towards this point, 1, 1. Like first of all, like right here in this first diagram, when you look at the curve near this point, it still looks like a parabola, but when you zoom in a little bit, it's starting to flatten out. And then finally, if you zoom in enough, it just looks like a straight line. So that's another way of thinking about differentiability of a function is that a function is differentiable at a point if when you if you can zoom in close enough where it looks like a line. It's in other words, right here it says in other words, the curve becomes almost indistinguishable from its tangent line. So the what you could say is a function is differentiable. Here's a way of thinking about differentiable functions. Again, I know I haven't introduced it, but here's a way of thinking about it. A function is differentiable if and only if it locally looks like a line. So like in other words, in the sense locally, in the sense like if you zoom in at the point enough, it'll look like a line, and any if you zoom in any further, it's just going to continue to look like a line. So that's kind of what it means to be differentiable. Locally, it looks like a straight line. And that's going to be a nice intuition because it's going to help us see why certain functions aren't differentiable. Um, so that's the tangent, that's a tangent line way of thinking about derivative, and then there's the velocity. Um, so here's another way. Okay, so notice in this definition, there's no h going to 0. It's x goes to a. It's that point. In other words, we're taking a point q, which is described as x comma f of x, and it's just going to be near this point. But there's no parameter describing what it means to be near, like we're used to seeing an h. And that's fine. You can reformulate this definition as follows. So basically, so here's another expression of the slope for the tangent line. So what you do is you now take h to be, you just introduce the parameter as h is equal to x minus a, and then if you solve for x, you get this. So first of all, then the slope of the secant line through um, PQ. So now so Q, remember, is the point x comma f of x. Well, we just solved for x in terms of h, so now Q can be described as the point a plus h comma f of a plus h. And now the slope of the tangent line, or secant line, I should say, through MQ from P and Q is described as that. So in other words, we've eliminated X and put in H in its place. And then note that as X approaches A, what happens as X approaches A? And just looking at that, well then H is going to approach 0, right? Because H is equal to X minus A. So in other words, as x goes to a, this implies, I don't want the comma. What this implies, so as x goes to a, this is going to apply h, which is defined as x minus a, is going to approach 0, right? Because if x is approaching a as a, then the difference should approach 0. Because in other words, x is getting really close to a. So if x is getting really close to a, then their difference should be getting close to 0. So h is going to 0. So this is another way of reformulating that definition of a slope of a tangent line. All right, so let me open up OneNote and we can look at this example right here. It's not OneNote. So I'll work through this example in OneNote. Actually, let me close these windows right here. So I don't want my computer to be overloaded, so I got to close Google. So let me end this task. All right. Hopefully that helps a little bit. All right, so what we want to do is we want to so this is example 3 in the book, and this is going to be find, oops, an equation of a tangent line at or let's say to the not parabola, but hyperbola, y is equal to 3 over x at the point 3 comma 1. So 3 comma 1 is definitely a point on this curve, satisfies the equation. And so we want to know the slope of the tangent line. So it's going to be, the slope is going to be m. It's going to be the limit as h goes to 0 of, so first of all, let's let f of x be, describe this curve. So it's going to be 3 over 8x. So we're taking the limit to find the slope. We're taking the limit of f of 3 plus h minus f of 3 divided by h, and then we do some substitution. So we get 3 plus h, sorry, not 3 plus h, but 3 over 3 plus h minus 3 over 3 all divided by h, and write this limit down. Now this 3 cancels to give you 1. So we're gonna have 1. So we're gonna just turn the 3 over 3 into 3h over 3h. So this, so I've kind of like thrown a bunch of steps in together, but 3 over 3 simplifies to 1, right? And then I can write 1 as this right here. So now we can combine the fractions in the numerator. And so the 3's cancel, and then we get h over 3h over h. And I guess, all right, now I'm going to multiply, well, I have a h in the numerator of the numerator, and then I have, so in other words, I have something like this. So this h right here cancels with this h right here, to give you 1 over 3 plus h. But if you don't like that, so that's one way of thinking about it. But if you don't like that, I can put in the step. So basically, you're going to multiply at this point 3 plus h over 3 plus h. So this 3 plus h cancels with that. And then, oh, I'm sorry, this is not h. We have 3 minus 3 plus h. So so you had to distribute this minus to this h to get negative h. All right. So now I distribute, so this 3 plus h cancels with this 3 plus h, and then in the numerator I have just negative h, and then in the denominator I have h plus 3h, 3 plus h. Now this h cancels with this h, oh, and this is as h goes to 0. So then what I have is negative 1 over 3 plus h. And now finally I can take this limit. This is a rational function. It's continuous at 0. So I can just plug in 0 to get this, which is negative 1/3. And no, I can't. So the answer is negative 1/3. So the slope of the tangent line is negative 1/3. And no, I can't just plug in 0 at this step. So if I plug in 0, I'll get 3 over 3 minus 3 over 3 gives you 0 in the numerator, which is not bad, but then I have this 0 in this denominator. So I have 0 over 0, and that's problematic. So that's what's called an indeterminate form, which we'll learn about later, actually. So this is negative 1/3. So this implies the slope of tangent line through the point 3 comma 1 is negative 1/3. And so now I have a point and I have a slope, so I can get the tangent line. So it's be y minus 1 is equal to negative 1/3 x minus 3. And I guess you can simplify it in any kind of way you want. I don't know. Let's see. It doesn't say to put the line in any specific form. I guess I'll just put it in the form that they put it. So I'm gonna multiply both sides by -3, so you get -3 plus 3 is equal to x minus 3. And then I'm going to add 3y and subtract 3. So then what you get is x plus 3y minus 6 is equal to 0. All right, let's see now. So now so these are the tangent line problem and instantaneous velocity or instantaneous rate of change are examples of derivatives. So let's just talk about derivatives more generally. So here's the definition. So we've seen this type of, as it says, we've seen a limit of this type arise in many different ways. It can, so for example, arise as finding the slope of a tangent line, or it can be arise as finding velocity of the vector. Um, but this limit of this form arises more generally whenever we just try to calculate the rate of change of in any kind of science or engineering, such as the rate of a reaction in chemistry or marginal cost in economics. So rates of change show up in lots of different contexts. So we want to be able to talk about rates of change of just rates of changes of just more general functions. And this is what's called the derivative. So you have function f, and then you can talk about the derivative of the function at a point A, and then we use this notation f prime of A, and it's defined as this limit right here, provided the limit exists. So it's going to turn out that not every function is differentiable. In fact, there are lots of functions, not hard to find functions that are not differentiable. They're not, in fact, they're kind of like the non-differentiable functions outnumber the differentiable functions. So when you have a differentiable function, it's very nice. It's sort of kind of rare in a sense. Um, it won't be rare for us because that's really all the functions that we're going to look at, but they non-differentiable functions do in fact exist. And as this notes down here, we can reformulate this definition in terms of a nearby point, x. So we just call x a plus h. So this will be x is a point near a. So that implies that more generally that this point in the plane is near a comma f of a. Oops. And again, when in fact, actually, we have something stronger than what we mentioned above. We have that h approaches 0 if and only if x approaches a. So this limit right here is in fact equivalent. It's equivalent to this right here. So these are the one and the same thing. They're gonna the number on the right hand side, if it exists, is the same as so the number on the right hand side of this. Oops. The of the right hand side, a number on the right hand side of this is in fact the same as the number on the right hand side of this. So we can use this common notation right here. There's no like ambiguity or worry about uniqueness or anything. This number this number on the left hand side is in fact equal to both of these limits. All right, so let's use it says definition 4. Oops. Compute this derivative right here. So let's do that. So this is example 4. We want to use definition 4 to compute. So we want to find derivative of f of x is equal to x squared. And this can now just represent anything. We're just kind of now being abstract, and that's the whole process of mathematics. Again, I've said this before, but you start with a concrete problem and you try to like extract and abstract the essential details of this problem so you can apply the ideas to a wider range of phenomenon. So now we're just talking about general functions. we have this function right here. We want to find the derivative at, well, there's the two parts. We want to find the derivative at the number 2, and we want to find the derivative at some number a. So we want to find the derivative at 2 and then a. All right. So let me see. The computer's freezing again. All right, so let's work on a first. So f prime of 2 is by definition the limit as h goes to 0 of f of 2 plus h minus f of 2 divided by h. And now we know f of 2, f of x is x squared minus 8x plus 9. So we have 2 plus h squared minus 8 times 2 plus h, and then plus 9, and then minus would be 2 squared minus 8 times 2 plus minus 9. Oh, sorry, this will be a plus 8 times 2 minus 9. You gotta make sure you distribute the negatives correctly. All right. So now we FOIL, so we get 4 plus 4h plus h squared minus 16 minus 8h plus 9 minus 4 plus 16 minus 9 divided by h. And if we simplify a lot, we get h squared minus 4h over h. And now I have a factor of h in the numerator and the denominator, so I can cancel, which is nice because I don't have to worry about getting 0 over 0 at this point. And you get h minus 4. And then you get, finally, when you let h go to 0, because this is a polynomial in h and it's continuous at 0. So you plug in 0, you get -4. Okay, let me see. I don't know why my computer's moving so slow. All right, let's see. I'm actually not gonna do part A. I'm gonna skip that. So I'll leave that. I'll let you do that one. What I'm gonna do is now example 5. So for example 5, we want to find the derivative of f of x is equal to square root of, 1 over square root of x. Let me just fix it. 1 over square root of x at some number a that's positive. So we're going to use definition 5 or equation 5. And so by definition, this is going to be the limit as x goes to a. So I'm not using the h parameter version. I'm using the other one, the other definition of the derivative. So it's going to be by definition this. Always write the definitions out before you use them. Don't just mentally apply the definition in your head. Write down the definition because that's the only way you're going to be able to memorize these things. So now the numerator is going to be 1 over square root of x and minus 1 over square root of a divided by x minus a. And now what we're going to do on another line is multiply by square root of a times square root of x. So we're going to multiply by square root of x times square root of a, and then of course if we multiply that by that, we have to divide by that, otherwise we change the fraction. And now if we distribute in the numerator, you get square root of a minus square root of x divided by so when I multiply this numerator through, I'm gonna just combine the square root of a and square root of x. So we square root of a times x and then times a minus x. All right, now again, I'm not quite there. If I try to let x go to a, I'm gonna get 0 over 0. So I need to do one more trick, and that's multiplied by the conjugate of the numerator. So when you do this, you're gonna get times the conjugate of the numerator, so the square root of a plus square root of x, and then you have to divide that by that, of course. And then when you do that, the numerator will be a minus x over, now I'm not going to combine everything in the numerator, I'm just going to leave it as a product. And sorry, the denominator will be this product, these three terms. Now notice the numerator is the negative of this term right here. So these two cancel out to give you -1. So the numerator cancels with this term right here. Then it's the negative of it. So when you cancel these two, you get -1, say, in the numerator. Doesn't matter, you can put the negative wherever you want. And then in the denominator, you're gonna have square root of a times x and times square root of a plus square root of x. And now notice when you let a go to 0 in this case, you don't get there's no problem. You don't get division by 0 or anything like that. So we can actually do the computation. Sorry, we don't need the limit symbol anymore. We can actually take the limit. This is going to be the thing we're taking the limit of is a continuous function, and its particular is continuous at a. So just plug in a. So you get right here, you get square root of a times a. So that's square root of a squared. So you get a. And then in right here, you're going to get 2 times square root of a. And then if you simplify that a little bit, you get 2 times a to the 3 halves. So now just kind of, I know that was a lot of steps, but just some time to appreciate how far we've come. Because remember, remember the original limit definition, that was epsilon delta, right? You had to do epsilon deltas. So what we've proven is the following. Hence we have shown that the limit as x goes to a of 1 over square root of x minus 1 this over x minus a is equal to -1 over 2 times a to the 3 halves. What does this look like in terms of epsilon deltas? Like, remember, this definition of limit is defined in terms of epsilon deltas. So if we didn't have all the tools that we had available to us, we would have to prove this using this epsilon delta definition. And that would look like the following. We would need to show that for every epsilon, there exists a delta that's positive. So epsilon is given, it's positive, such that if x minus a is less than delta, it implies that 1 over square root of x minus 1 over square root of a, so the function divided by x minus a minus, so minus but plus 1 over 2 a to the 3 halves is less than epsilon. And you can see this is really horrible. Who would want to do this? This is a really horrible problem. It's doable. It's completely doable. We know that this limit exists. We just calculated it and we know what it's equal to. So in principle, if I give you an epsilon, you should be able to find a delta that makes this implication right here, this implication right here, true. But it's going to be really horrible. So take some time to appreciate how far we've come in just this little time. We started with this epsilon delta formulation of what a limit is. We give a rigorous meaning to what it means to take the limit of a function. It was cumbersome, but we were able to deduce some general rules that allows us to solve a wide range and wide variety of problems, particular this one. And if you didn't have those tools and machinery and techniques at your disposal, which are, again, they're sort of annoying to go through to prove, but you can see that they're immensely helpful because without them, we would have to solve this problem like this. We'd have to justify this using this epsilon delta. But thanks to the fact that we've developed the theory of limits, we don't have to do this. We can avoid having to go through this awful calculation right here, figure out what delta is. I have no idea what it would even look like. I'd have to go through the sum. I haven't even solved a problem like this, honestly. There's no point in solving a problem like this. Um, at least I have not had any need to solve a problem like this ever. But thanks to developing the theory of limits, we don't have to. We can use some tricks and techniques like multiplying by a conjugate, adding fractions together, and then using all our limit laws to compute these. All right, so let's see what else we have in this section. So I just want to just do a little detour to give you a sense of how far we've come and how awful these calculations can get using those definitions. So it would behoove you to develop the theory of limits to simplify these calculations in the way we have. All right, let's see. My book computer is freezing again, so just gotta give this a little bit of time, I guess. I don't know why it's freezing. I'm gonna stop sharing for a second, figure out why this is freezing. All right, it seems to be working out, so let me share my screen again. So there's just one last thing I want to show you in the book, and then that'll be all. Like just one or two more things. Just two more things actually. Um, so this right here, this statement in the box is just a summary of what we've done so far. So if you have a curve, you have a function, you can draw a curve associated to it, and you can talk about a tangent line to this curve at this point. And what we've seen is that the tangent line through this point right here, has slope equal to the derivative. The derivative just is the slope of this tangent line. And so what that means is that if we want to find the point slope form of this equation of this tangent line, and it goes through this point, it's going to have this form right here. This is the slope. All right, and then well, we went through this example already. Actually, I think we went through this exact example. We computed this. We found the tangent line, I think, actually. Oh no, what we did. So here's this. We looked at this function already, this curve. And then we found that well, we didn't go through this calculation. So this calculation you should go through on your own, read through it. Not that hard. This is from example 4B. We just went over 4A. If you compute the derivative of the function at A, you'll see that it's given by the following formula, 2A minus 8. And so if you want the slope, just plug in of the tangent line at this point, just plug in A to the derivative and you get -2. And then so that implies that the slope of this tangent line is going to look like that. Actually, now I'm realizing there's one thing I didn't show um, when we went over the hyperbola example. Let's see. Right here. We went through this example. F of x is equal to 3 over x. We wanted to find the slope of the tangent line at this point of this curve. We went through this calculation, found that was -1/3. And so here's just a little visualization. So the blue curve is the curve 3 over x. So it just looks like function 1 over x. You can't really tell the difference, honestly. 1 over x, 3 over x, 5 over x, 100 over x, they all basically look the same. They have this shape right here given by the blue curve. And then the red curve is going to be the tangent line. So it's going to, and it's described by this equation right here. All right, so now that was one thing forgot to show you. And then let's go back down here. Yeah, so this is just another way of expressing the slope of the, or sorry, this is right here is another way of writing the equation of the tangent line. Now that we know that the derivative just is the slope of the tangent line. It's by definition the slope. And then just one last way of thinking about derivatives. So here's the discussion. It says that suppose we have some quantity y that depends on another quantity x, which is uh, just anything you do in science, say. You're always, or even in mathematics, you're always thinking about how one quantity depends upon another quantity, or one thing more generally depends upon another thing. Um, so what we're saying, another way of saying that is that y is a function of x, so we can write this. So the f describes the dependence of y on x. And now we can think about x changing. It says x is a variable, so it can change from x1 to x2. And then we can talk about this increment, this delta x. This is going to be like the change in x. It's going to be this, it's going to be the change in x, or also called the increment of x. And then we can look at, so now because y depends upon x, we can look at how y changes as x changes. So we talk about the delta y. And then notice the difference quotient, the of the quotient of delta y over delta x is just this different quotient that we've been looking at. It's like basically the derivative. This is going to be our average rate of change of y with respect to x on this interval. So this should look all very familiar if you remember lecture 2.1. We were just talking about like T1 and T2, and we were talking about P of T. We were thinking about position of a particle, but this is the exact same discussion. This is the power of abstraction in mathematics, that those concrete problems you're looking at contain all the essential ideas for your general theory. So now we have the average rate of change of y with respect to x over this interval, and then here's just a way of visualizing it. So this is the same sort of, so this is this the same sort of graphs we've been looking at, just decorated differently. Now with this notation delta x and delta y, but same sort of picture, just different notation. And then we could talk about the instantaneous rate of change as the limit as delta x goes to 0. So delta x goes to, so remember x is equal to like x1 minus x2, and then sorry, no, um that's not right. Let me just make so we're thinking about x changing from um thinking about x changing from between x1 and x2, and we call that delta x. And so when so if delta x is equal to x1 minus x2, then we can say that delta x approaches 0 if and only if x1 approaches x2, or equivalently x2 approaches x1. Either way, you get the same type of idea. If the difference if the difference is becoming small, it's approaching 0, then that means these points are approaching each other. Either one is fixed and the other approaches it, or vice versa. One of them might be fixed and the other one approaches it. And so the limit, this is just another way of expressing the limit. It's delta x over delta y. And this is going to be helpful when we talk about differentials. Now, this is just one of the optional sections. There won't be a homework on differentials, but I do want to talk about differentials because they're going to be helpful when when we get to integration and we talk about u substitution. So differentials are helpful in making sense of this idea of u substitution for computing integrals. But of course, that's way, way in the future, so don't worry about that. Just know that we're going to talk about differentials at one point, but there's not going to be a homework on them. We just need them to talk about something else. Um, Yeah, so this is just all different ways of expressing the exact same thing. So yeah, so the derivative f prime of a is the instantaneous rate of change um of this function with respect to x when x is equal to that. So all these ideas should be somewhat familiar. I think that's it. The connection with the what does this say? So the connection with the first interpretation is that if we sketch the curve y is equal to f of x, then the instantaneous rate of change is the slope. So the instantaneous rate of change is the slope of the tangent line to this curve at the point where x equals a. Um, so these are just two ways of thinking about the same thing. They have this tangent line approach to thinking about derivatives, where you have this instantaneous rate of change. And the connection is that the instantaneous rate of change just is the slope of the tangent line, and vice versa. The slope of the tangent line is the instantaneous rate of change. And if this is like, if you want a mental picture and you're saying, oh, what is instantaneous rate of change of what? Just think of the particle and the motion. That's like the best. It's always good to have a toy model in your mind when you're thinking about these concepts. And if I mean, you can have your own toy model. If you don't like thinking about particles moving along the line, come up with your own model. But I think that's the easiest thing to imagine, like the particle or the car. I think we looked at an image of a car moving forward and backwards. So always good to have a mental picture. So that's what we mean by instantaneous rate of change. For example, we could talk about velocity. All right, I think that's it for now. So I'm gonna stop sharing and I'll upload this right away.